formation takes place in the densest region of giant molecular cloud. This dense clump becomes gravitationally unstable and begins to collapse, giving rise eventually to the formation of new stars. Once formed, massive stars quickly begin to affect the surroundings through intense radiation and stellar winds, reshaping and often disrupting the parent cloud. Over time, the continued injection of momentum and energy from the young massive star disperses the remaining gas. The early stage of star formation are often so deeply embedded in their natal material that they are undetectable in ultraviolet or optical wavelength and often only visible in the infrared or longer wavelength. Here we will focus on star clusters in this early stage in which they are still surrounded by gas and dust from their parent cloud. Before JWST, this kind of object had only been studied in our own galaxy, the Milky Way, or in nearby systems as the Magellanic Cloud. Now, thanks to JWST, we can observe them in much more distant galaxies. With JWST NIRCam, we are reaching a spatial resolution better than 10 parsec in galaxies as distant as 20 megaparsec, which is the range of distance covered by the PHANGS-JWST Cycle 1 sample, which observed 19 galaxies between 5 and 20 megaparsec. In particular, we identify this dusty young object by detecting compact sources that emit at 3.3 micron. This is one of the characteristic emission features of the polycyclic aromatic hydrocarbon, or PAH. PAH are organic molecules made of carbon and hydrogen atoms arranged in aromatic rings, and they get excited when they absorb ultraviolet photons from young stars, and then they remit that energy in the infrared, producing a series of emission features. In particular, the 3.3 feature is associated with a very small PAH grain. Before JWST, this particular feature hadn't been studied in much detail. It was not covered by a Spitzer infrared spectrograph, and although it was captured by its camera IRAC-1, the band was too broad to easily isolate it. Now with JWST, we can capture this feature with the F335M band and with much better resolution. So, as I mentioned before, F335 captures the 3.3 micron, while 300 captures the underlying continuum. That means that we can use color, in particular F300 minus S335, to detect sources with a significant 3.3 excess. In this color magnitude diagram, sources that fall in the right side of the curve are sources with a significant 335 color excess, indicating a strong 3.3 PA emission. We applied this selection method across all 19 galaxies in the PHANGS-JWST Cycle 1 program. To clear out our initial sample, we also use the F1000 minus F2100 and F335 minus F360 M color to remove potential contaminant, specifically red evolved star, which can also appear bright in the infrared. After applying these criteria, we identify over 1800 compact sources with clear 3.3 micron PA emission. This is the northern region of the galaxy NGC 3627, located at about 11 megaparsec. If we zoom into this small red box, we can explore the region across different wavelengths. Using PHANGS-HT, PHANGS-H-alpha, and PHANGS-JWST, we have a spectral coverage from the ultraviolet at 2700 angstrom to the mid-infrared at 21 micron. Looking first at the HGST visible image, one of the key things that we notice is that the 3.3 micron PA emitter tend to lie along a dust lane. Some of them, like option number 2, 3, and 4, are completely invisible in the HGST broadband filters. Others, like option number 5, don't show up at shorted wavelength but start to appear in the H-alpha and become very bright in the infrared. Some others, like option number 1, are clearly detected even in the HGST visible band. But what they all have in common is that they are clearly detected in the infrared and they become progressively brighter as we move at longer wavelengths. Now, if we look at where these objects are located within the galaxy, we find that they appear primarily along the dust lane, spiral arm at the end of the bars. We don't see them in the bars themselves, which is interesting. They also tend to show up in the inner star-forming rings and in the central region of the galaxies. As I mentioned earlier, we identified more than 1,800 compact sources with 3.3 micron pH emission. We measure the concentration index, or Ca for short, of these sources. The Ca gives us an idea of how compact a source is. Point-like sources like a star have low Ci, while unresolved star clusters are slightly more extended with higher Ci. When we compare the Ci values of our 3.3 micron parameters with those of known star and star cluster in each galaxy, we find that they match the range expected for star clusters. This tells us that these pH emitters are likely very young star clusters. Interesting, when we compare the 3.3 pH emitters with the PHANGS-JWST cluster catalog, which are clusters identified in HGST optical wavelength in previous work, we found that the overlap between both catalogs was less than 10%. This means that over 1,600 of our PA emitters are new detection. The cluster in the PHANGS-JWST catalog have edges derived through SED fitting, so we took the coordinate of the cluster in these catalogs and performed photometry in the JWST bands and then placed them in this 300-335 color magnitude diagram, grouped by different ages. When we look at clusters younger than 3 million years, we see that some of them do show 3.3 micron excess. Some of them fall in the region of the 3.3 emission. But when we move to slightly older clusters between 4 and 10 million years, almost none of them fall in this region. In other words, they no longer show 3.3 micron per emission. Here, I'm just showing the CMD for NGC 1672, but we observed this same behavior across all the 19 galaxies. So, evidently, the 3.3 pH emission at cluster scale lasts for a very short time, less than 3 million years. And this is important because it means we are seeing a cluster before any supernova have exploded. So, pre-supernova mechanisms as stellar wind or radiation pressure had to play a key role in clearing out the dust and gas around the cluster. We also measured the H-alpha equivalent width for both the HGST cluster binned by age and the 3.3 micron pH emitters. To do this, we need that the cluster to be visible in H-alpha and the Franklin band. So we were only able to do this in the 3.3 pH emitters that were visible in HGST. We found that the compact 3.3 pi emitter shows H-alpha equivalent width about 1 to 2.8 times greater than those of the younger optical detected PHANGS-JWST clusters. H-alpha equivalent width is a well-known age indicator for young stellar population, so this result indicates that, on average, pH emitters are even younger than the youngest cluster detected in HGST. So, in summary, the resolution and sensitivity of JWST allows the detection and characterization of dusty, very young star clusters in external galaxies, something that was not possible before. The 3.3 micron pi emitters seem to be a good tracer of dust-embedded star clusters. We identify over 1,800 compact sources across the 19 nearby galaxies in the PHANGS-JWST Cycle 1 program. Most of these are new detections. The pH emission at cluster scale disappeared very quickly, less than 3 million years. These sources also show high H-alpha equivalent width, even higher than the youngest cluster seen in the optical, and pre-supernova mechanisms had to play a key role in clearing the dust and gas around the clusters. Thanks for watching, and don't forget to follow for more fun science.